Bismillahirrahmanirrahim. Assalamu alaikum, students. Today, our topic is dielectrics and atomic theory. Remember, in last lecture, we explained the effect of filling the space between the capacitor with dielectric, and we defined the dielectric constant. Dielectric constant of a given dielectric is defined as C over C naught, where C naught is the capacitance of the capacitor with vacuum or air between the plates, and C is the capacitance of the same capacitor with the dielectric between the plates, assuming all the space between the plates is filled with the dielectric. So C is greater than C naught, because K is greater than 1. For vacuum, K is dielectric constant is 1. And we said there are two ways we can insert a dielectric between the plates of a capacitor. In one way, we charge the capacitor, disconnect the battery. In that case, the charge on the plates of the capacitor remains constant. And when we insert the dielectric between the plates, potential difference reduces. That leads to reduction in the reduction in the potential difference when we insert the dielectric, and the capacitance increases. Second case is when we keep the battery connected, we ensure the potential difference between the plates of the capacitor remains constant. And when we insert, in that case, the dielectric between the plates of the capacitor, charge on the plates of the capacitor increases. That leads to the increase in its capacitance. We have discussed in this thing in detail in last lecture. Now, in this lecture, we want to understand the behavior of dielectric with regard to increase in the capacitance of a capacitor by its insertion between the plates of the capacitor in atomic terms. We want to understand what happens at the atomic level in a dielectric when we place a dielectric in an electric field. So dielectrics are of two kinds. Accordingly, there are two possibilities when we place a dielectric in an electric field. Remember, when we are inserting dielectric between the plates of a capacitor, when it is charged, we are actually placing the dielectric in the electric field, because there is an electric field between the plates of a capacitor when it is charged. So dielectrics are of two kinds. One is polar, second is non-polar. Now, in case of polar dielectric, for example, water, the molecules of water have permanent electric dipole moments. Write it. Molecules of water have permanent electric dipole moments. Remember the definition of electric dipole moment. Electric dipole by definition is a pair of two equal and opposite charges separated by certain distance. For example, if I have plus q charge and minus q charge separated by certain distance, then it forms, let the distance between them be d, it forms an electric dipole. And we define an electric dipole moment for a dipole. We denote that by P and define it at magnitude of either charge of the charges times the distance of separation. And remember, we define it as a vector, where the direction of the electric dipole moment is along the axis of the dipole pointing from negative to positive charge. So we define this separation between the charges as a vector like this, d vector. So electric dipole moment becomes then q times d. This is definition. So the polar dielectric, like water, has a property that its molecules have a permanent electric dipole moment, and where from it comes from its structure. Now, in such molecules, that means in case of polar dielectrics, what happens when we place the dipoles in the external electric field? When they are outside electric field, these dipoles in it are randomly oriented. So this is the situation when there is no external electric field, no external electric field, right? When you place such a dielectric in an external electric field, let there be some electric field E. What happens? Let me name it E naught. These dipoles become oriented. This is in the presence of electric field, external electric field. So these dipoles become oriented in the direction of the applied field. Now, because the molecules are in constant thermal agitation, the degree of alignment is not complete, but increases as the applied electric field increases or as the temperature decreases, right? In the absence of an electric field, the dipoles are randomly oriented. This is one possibility for polar dielectrics. I want to understand what happens to non-polar dielectrics when they are placed in an external electric field. Remember, if we have an atom, this be some its positive charge, and then there is the electron cloud. It's an atom. If it is outside electric field, the center of positive charge and the center of negative charge coincide, so its dipole moment is 0. But if you place it in an external field, what will happen to this atom? The positive charge will experience force in the direction of the electric field. Remember, F is equal to QE. The charge Q is placed in an external electric field E. It experiences an electric force given by QE. So positive charge experiences force in the direction of the electric field. Negative charge experiences force opposite to the direction of electric field. So the atom gets polarized. Now there is the center of positive and negative charge do not coincide, right? So there is creation of an electric dipole moment. This kind of electric dipole moment is called induced electric dipole moment. Right? The same is the situation in case of non-polar dielectrics. Their molecules do not have permanent electric dipole moments, but they acquire them by induction when placed in an electric field. Right? Now this induced electric dipole moment is present only when the electric field is present, and it is proportional to the electric field for normal field strengths and is created already lined up with the electric field, right? Polar dielectrics can also acquire induced electric dipole moments in external electric fields. You should remember it. Polar dielectrics can also acquire induced electric dipole moments in external fields. right? So now let us use a parallel plate capacitor carrying a fixed charge Q. Let us use a write it neatly. Let us use a parallel plate capacitor carrying a fixed charge Q, a fixed charge Q, and not connected to a battery. Provide a uniform external electric field E naught into which we place a dielectric slab, into which we place a dielectric slab. As shown in figure 1. We draw the figure. We complete the figure first. We complete the figure. This is my figure 1. This is part A, this is part B, this is C. So in part A, a dielectric slab exists, but applied electric field is 0. Now the circle suggests the spherical shape of neutral atoms within the slab. In part B, an external electric field E0 separates the positive and negative charges of the atoms. But an element of volume in the interior of the slab contains no net charge, but there is a net induced surface charge on the slab, negative on the left side and positive on the right side. In part C, let me first explain this. What is E prime? E prime is the electric field created by the induced surface charges created on the opposite faces of the dielectric slab. So this electric field E prime is opposite in direction to the applied electric field E naught. So in the interior of the dielectric slab, the net electric field is E, which is vector sum of E naught and E prime. So you can understand the overall effect of alignment and induction is to separate the center of positive charge of the entire slab slightly from the center of negative charge. I repeat, although the slab as a whole remains electrically neutral, it becomes polarized as suggested by figure 1b. The net effect is a build-up of positive charge on the right face as already described of the slab and negative charge on the left face. Within the slab, no excess charge appears in any given volume element. Now, since the slab as a whole remains neutral, the positive induced surface charge must be equal in magnitude to the negative induced surface charge. I write it, you must remember it. Since the slab as a whole remains neutral, the positive induced surface charge must be equal in magnitude to the negative induced surface charge. Note that in this process, electrons in the dielectric are displaced from their equilibrium positions by distances that are considerably less than an atomic diameter. There is no transfer of charge over macroscopic distances, such as occurs when a current is set up in a conductor, right? Now figure 1c, that is this figure, shows that the induced surface charges, these negative charge and this positive charge, always appear in such a way that the electric field E prime set up by them opposes the external electric field E naught. The resultant electric field E in the dielectric is the vector sum of E naught and E prime. It points in the same direction as E naught but is smaller. So the conclusion is, if we place a dielectric in an electric field, induced surface charges appear which tend to weaken the original field within the dielectric. Let me write it so that you can remember it. So conclusion is, if we place a dielectric in an electric field, induced surface charges appear which tend to weaken the original field within the dielectric. This weakening of electric field reveals itself as a reduction in potential difference between the plates of a charged isolated capacitor when a dielectric is introduced between the plates. Remember the relation V equal to ED, D being the separation distance between the plates of the capacitor, V the magnitude of potential difference, E the electric field. This relation V equal to ED for a parallel plate capacitor holds whether or not dielectric is present. And this equation shows that the reduction in potential difference I had already discussed in last lecture is directly connected to the reduction in electric field E as explained in this lecture. Both E and V are reduced by the same factor Ke. Remember, this holds only when battery is no longer connected. If the battery remains connected, the potential difference V would be constant, but Q, the charge on the plates, would increase. The increased electric field from this additional charge on the capacitor would be opposed by the field E prime in the dielectric, and the result would be a constant electric field E. I repeat, if the battery remains connected, the potential difference would be constant, but charge on the plates of the capacitor Q would increase. The increased electric field from this additional charge on the capacitor would be opposed by the electric field E prime in the dielectric, and the result would be a constant electric field E, right? So this is how we explain the behavior of the dielectric between the plates of a charged capacitor on atomic terms. Let us move to next topic, dielectrics and Gauss's law. So far, we have used Gauss's law in the situations in which no dielectric was present. Now let us apply this law to a parallel plate capacitor filled with a material of dielectric constant Ke, or you write it kappa E. Let me draw the figure first. Complete the figure. Let me complete the figure. The color, now we choose green color. This is figure 2. This part A, this part B. Let me explain it. So this figure 2 shows the capacitor both with and without the dielectric. In part A, I have a parallel plate capacitor which is charged. So plus Q is charge on one plate, minus Q is charge on the other plate. There is no dielectric between the plates. So the electric field between the plates of the capacitor is E naught and it is downward. I have shown a Gaussian surface enclosing the positive charge. It is of cubical shape, and this figure shows the parallel plate capacitance cross section, remember, right? In figure 1b, 2b, a dielectric slab is inserted between the plates of the capacitor while the charge Q on the plates remains constant because we have disconnected the battery. uh, Ke is the dielectric constant of the dielectric. As shown in the figure, induced charges Q prime appear on the surface of the dielectric slab. Minus Q charge appears on this surface, which is close to positively charged plate, and plus Q prime induced surface charge appears on the other surface of the dielectric slab, which is close to negatively charged plate, right? And we have again shown a Gaussian surface. It encloses the positive charge on the plate and induced negative charge on the surface of the dielectric slab. And we are showing electric field within the dielectric as E, which is smaller than E naught. So I have shown this vector smaller, right? Now, if no dielectric is present, right? If no dielectric is present, that is figure 2a, we have no dielectric in this figure. Gauss's law gives, apply Gauss's law. Epsilon naught closed integral E dot dA is simply epsilon naught E naught A equal to Q, or E naught is equal to Q by epsilon naught A. Let me name it as equation first. We haven't used any equation. This is our equation 1. It's my equation 1, right? What is A? A is area of the plates. Area of the plates of the capacitor. You know that. I'm just refreshing it. So when we calculate this flux through the Gaussian surface, only this lower face of the Gaussian surface will contribute. That is just E naught A, right? So we have solved for the electric field between the plates of the capacitor E naught as Q by epsilon naught A. Now let us move to situation second. If the dielectric is present, that is figure 1 2b, this situation is figure 2b. I'm skipping the pages. Gauss's law gives epsilon naught closed integral E dot dA is equal to epsilon naught EA is Q minus Q prime, or E is equal to Q by epsilon naught, it's E here, minus Q prime by epsilon naught E. Let me name it equation second. Let me explain it. Here we apply Gauss's law. Epsilon naught times closed integral E dot dA. It will be epsilon naught EA, not E naught, because electric field here at the surface of the Gaussian surface is E, not E naught. And the charge inside this Gaussian surface is Q plus minus Q prime. The net charge inside the Gaussian surface is Q minus Q prime. I have enclosed the negatively charged surface of the dielectric as well within the Gaussian surface, right? So we have E equal to Q by epsilon naught A minus Q prime by epsilon naught A, in which, I repeat, minus Q prime is the induced surface charge right? And Q is the free charge on the plates. So you need to distinguish these two charges. Charge on the plates Q is called free charge, and the induced surface charge is sometimes called bound charge, right? Let us move forward. The dielectrics, as already discussed, the dielectrics reduce, I should say here I'm using dielectric. The dielectric reduces the electric field by the factor Ke, and so E is equal to E naught by Ke, which is Q by Ke epsilon naught A. Let me name this as 3. This is my equation 3rd. E is the electric field within the dielectric. E naught is vacuum electric field. We know E is E naught by Ke, and from first, this is my first, E naught is Q by epsilon naught A. So I have written it, E is equal to E naught by Ke. I have substituted for E naught Q by epsilon naught A. So I got E is Q by Ke epsilon naught A. This is my 3rd. Now inserting this 3rd equation into 2nd. So substituting or inserting equation 3rd into equation 2nd, we get, it is simple. I put this here. What I get? I get Q by Ke epsilon naught A equal to Q by epsilon naught A minus Q prime by epsilon naught A. I have got this and put it here. So I got this equation. Q by Ke epsilon naught A is equal to Q by epsilon naught A minus Q prime by epsilon naught A, or we can solve it. 1 by epsilon naught A, you can take common and that will get cancelled. Then you solve, get Q prime is equal to Q times 1 minus 1 by Ke. Name it. This is my equation 4, right? So this is my 4. This equation 4 shows that induced surface charge Q prime is always less than Q. I repeat, this shows that induced surface charge is always less in magnitude than the free charge Q and is equal to 0 if there is no dielectric present. Remember, if there is no dielectric, Ke is 1, 1 minus 1 is 0, so there is no bound charge or induced surface charge. Now, if there is dielectric, then induced surface charge group Q prime is less in magnitude than the free charge Q. Right? This was one conclusion. Next, we write Gauss's law for the case of figure 2b. Now, we write Gauss's law for the case of figure 2b, that is this case, when dielectric is between the plates of the capacitor. So I write it in the form epsilon naught closed integral E dot dA is equal to Q minus Q prime. Let me encircle it. Name it as 5. Q minus Q prime, again being the net charge within the Gaussian surface. Now, substituting from 4 for Q prime, I'll write using equation 4 in equation 5, we get this 5 here, right? What I do, I took this value of Q prime from equation 4 and substituted in equation 5. And after some rearrangement, what we get epsilon naught closed integral Ke E dot dA is equal to Q. This is my equation 6. I have taken this Q prime value as Q times 1 minus 1 by K, substituted here. Then when you make, you simplify the things, you get this equation 6. This important relation, this equation 6 is an important relation. Although we derived it for a parallel plate capacitor, it is true in general. It is true generally and is the form in which Gauss's law is written usually written, or when I should write usually, when dielectrics are present, right? Now the flux integral, this, let me use another color. We need to note in equation 6, first thing, the flux integral now deals with Ke instead of E. You have here Ke instead of E. This is consistent with the reduction of electric field E in a dielectric by the factor Ke, right? Okay. Second thing, the charge Q contained within the Gaussian surface is taken to be the free charge only. Induced surface charge is deliberately omitted on the right hand side of equation 6. And that is taken into account by the introduction of Ke on the left side. Now, equation 5 and equation 6 should write equations 5 and 6 are completely equivalent formulations or completely equivalent formulations. You can write Gauss's law when dielectric is present as using equation 6. It is in terms of only free charge, but there is dielectric constant in the integral on the left hand side, or you can write it in terms of equation 5. There is no dielectric constant on the left hand side, but there is, in addition to free charge Q, an induced surface charge on the right hand side of this equation, right? I will give you a homework now. The question says, let me draw the figure first. It has a figure. This is plus Q. This is minus Q. Then there is a dielectric slab. It has width B. Total separation distance between the plates of the capacitor is D. And next, we named figure 3. We'll use figure 2 here. Let me write the question. The question says figure 3, that is this figure, shows a parallel plate capacitor of plate area A and plate separation D, right? And question says potential difference, a potential difference V naught is applied between the plates. The battery is then disconnected and a dielectric slab of thickness B and dielectric constant kappa E or K is placed between the plates as shown. Assume A is equal to 115 centimeter square, B equal to 1.24 centimeter, B equal to 0.78 centimeter, the electric constant equal to 2.61, V naught equal to 85.5 volt. Part A, what is the capacitance C naught before the slab is inserted. So part A. Part B, what free charge appears on the plates? This is part B. Then part C. What is the electric field? What is the electric field E naught in the gaps between the plates and the dielectric slab and the dielectric slab. This is part C. Then I have part D. Calculate the electric field E in the dielectric slab. Then I have part E. What is the potential difference between the plates after the slab has been introduced? The last part, F. What is the capacitance with the slab in place? Let me check the question. First, I will check my figure 3. Okay. The question says, figure 3 shows a parallel plate capacitor of plate area A and plate separation D. The potential difference V naught is applied between the plates. The battery is then disconnected and a dielectric slab of thickness B and dielectric constant Ke or kappa E is placed as shown, placed between the plates as shown. This is a dielectric slab here. Its dielectric constant is Ke, right? As placed between the plates as shown, assume A equal to 115 centimeter square, D equal to 1.24 centimeter, B equal to 0.78 centimeter, KE or kappa equal to 2.61, V naught equal to 85.5 volt. Part A, what is the capacitance C naught before the slab is inserted? What free charge appears on the plates? That's part B. Part C says what is the electric field E naught in the gaps between the plates and the dielectric slab. Then I have part D, calculate the electric field E in the dielectric slab. Part E says what is the potential difference between the plates after the slab has been introduced. And part F, what is the capacitance with the slab in place. That's all for today. Do your homework, uh, complete your notes, learn at your pace, and don't waste your time. And do not forget to subscribe my channel. Thank you. Assalamu alaikum.